Now it's time to solve some actual systems of equations. So we can use matrices to do this. And this is what we're going to use for the rest of our time, solving systems of equations. So we'll need a little bit of background in matrices. We'll talk about some other ideas in the next lecture that are a little more complicated. But for now, we'll just need kind of the bare basics of matrices. Let me give an example of a system of equations. Let's say we have something like this. X1 prime equals 2x1 minus 6x2, x2 prime equals negative x1 plus 3x2. All right, so again, a coupled autonomous system, like the ones we looked at before. We've drawn phase portraits for them now, and now we're getting ready to solve them. So we're going to rewrite this as a matrix equation. So to rewrite this in matrix form, it would look like this, where the left-hand side would be a vector of these two derivatives, x1 prime and x2 prime. And then we would have the matrix of coefficients. So that would be 2, negative 6, negative 1, and 3. And then we'd have a vector x1 and x2. So just as a reminder, in case you haven't seen this in a while, hopefully you've seen this before somewhere, but if you're multiplying matrices, like if you have something like this, the way you would do this is you would take this row multiplied by this column, and then this row multiplied by that column as well. And so you would take A times x1 plus B times x2, and then you would do the same thing with the second row. You take C times x1 plus D times x2. So what it boils down to is if you write them with the same variable in the same column, you can just sort of pick out these coefficients to be in this matrix of coefficients. So we've got a matrix of coefficients, and it's 2 by 2 because we have two equations and two functions we're working with, x1 and x2. So the two equations means we have one row for each equation, and the two variables means we have a 2 by 1 vector of solutions, and so we need a 2 by 2 matrix to multiply by that. So matrix multiplication, you have to have the dimensions match up carefully so that you can multiply them like this, but the bottom line for us is that you can take a system like this and extract out the coefficient matrix, and that's kind of the significant piece to all of this, is that coefficient matrix. That's what controls the behavior of the system for different values. We'll talk about what different kinds of systems can look like. We're going to stick to relatively simple ones that look like this system here. I'll show you some other variations, but the ones we actually get around to solving will look just like this. And basically just the values of those coefficients is going to control the behavior of the system. So that's the significant piece. So I'm going to show you a couple other examples of some systems of equations and how to write them as matrix equations. But once we do that, then we'll revert kind of back to this to actually solve them. So let me show you another example here, a little more complicated one. We have something like x1 prime equals 2x1 plus t squared x2 plus 4t plus e to the t x3. x2 prime is sine of t times x2 plus cosine of t times x3. x3 prime is x1 plus x2 plus x3. The question is how to write this as a matrix system. And again, if you want to pause the video and practice this on your own to see if you can do it, that might be a good idea. But to do this, the left-hand side is just going to be the vector of derivatives, x1, x2, and x3 prime. And then on the right-hand side, we're going to have a matrix of coefficients, or what's multiplied by x1, x2, and x3. And so in the first equation, what's multiplied by x1 is 2. What's multiplied by x2, that's t squared. And what's multiplied by x3, that's the 4t plus e to the t. Then in the second equation, what's multiplied by x1, that would be 0, since there's no x1 there. And then x2 gets multiplied by sine of t, and x3 gets multiplied by cosine of t. And then the last row, x1, x2, and x3 are all multiplied by 1. So there's your matrix representation of the system. So it's helpful to be able to translate a system of equations like this into a matrix setup. And the reason is that when we get to solving them, that's what we'll start with. So both of these examples are, both the ones you've seen before, are homogeneous, right? Because there's no extra forcing function multiplied on or added on at the end, rather. Here's an example of one that isn't. So say, for example, we have something like x1 prime equals 2x1 minus 6x2 plus sine of t, and x2 prime equals negative x1 plus 3x2 minus 7. That would look like this, where you have your left-hand side is x1 prime, x2 prime. The coefficient matrix would be 2, negative 6, negative 1, 3, just like the first equation. But then also added at the end, the first equation has a sine of t added to it. The second equation has a negative 7 added to it. So you have this non-homogeneous part because you've got extra stuff added on at the end. So let me give you the general structure of one of these. So in general, you can write a system of equations this way, where you have x prime and you have a vector x prime. So this vector includes x1 prime, x2 prime, and so on. So x prime is x1 prime all the way down to whatever n is, however many you have. So however many equations you have in your system, that's how many rows you have in this x prime vector. And then you have a coefficient matrix times x. So x again is a vector, x1, x2, down to xn. Again, for as many equations as we have, that's how many solutions we're looking for, x1 through xn. So that's an n by 1 vector. And then you have this matrix of coefficients. And that's going to be n by n, right? It's going to be a square matrix because you have the same number of equations as you do solutions to find. If you didn't, we wouldn't be able to solve it. And then potentially you can have some vector of forcing functions, f of t. So you'd have like f1, f2, and so on, one for each equation that you have. So that's the general setup. Now, for our purposes, we're going to keep things relatively simple. First of all, A will be just a matrix of constants only. So only have constant coefficients. And then also we're going to deal with homogeneous cases. So we're going to assume that this forcing function matrix or vector is 0. So the homogeneous case. If you wanted to solve non-homogeneous ones, you can use undetermined coefficients, for instance, to do this. So it is possible, but it just adds on more than we want to tackle at once. So if you look at the 3 examples we've seen so far, only that first one matches the case that we're going to look at, because it's got constant coefficients and it's homogeneous. The second one is homogeneous, but it doesn't have constant coefficients because there's t's in the A matrix. And the last one is constant coefficients, but then it's non-homogeneous. Sorry, there should be, I just noticed this, there should be a vector x1 and x2 here. There we go. So here you've got x prime equals ax plus f of t. So the A is the matrix 2, -6, -1, 3, and the F matrix is the sine of t, -7. All right, so there's our setup. So our general structure, our picture is just going to look like x prime equals ax. That's our problem to solve. That's what we're going to tackle. So for example, we can do an example with a spring problem. So an undamped, unforced spring. So of course the fact that it's unforced is necessary because we're dealing with the homogeneous case. The undamped is just coincidence. So if you have something like my double prime, normally there'd be a by prime term, but if it's undamped, that isn't there. And then ky equals 0 because it's unforced. So if we want to write this as a system of equations, like we talked about in the last lecture, you would define new variables. You have x1 equals y and x2 equals y prime. So in our system, we would have x1 prime equals x2 and x2 prime equals y double prime. And so we want to rearrange this equation to solve for y double prime. So we have negative k over m y, which makes our system of equations look like this. We have x1 prime equals x2 and x2 prime equals negative k over m x1, which, if we write that as a system of equations, would look like this. Our coefficient matrix, the first one is 0 times x1 plus 1 times x2. The second equation is negative k over m x1 plus 0 x2. So if we write this as x prime equals ax, sorry, x prime equals ax, A would be this coefficient matrix right here. And so we're going to talk about how to solve systems like this using some matrix methods to solve, but all of them are going to fit this same format where you have x prime equals ax. And so the only thing that's going to change from one problem to the next is what this matrix of coefficients looks like. And we'll see how different values in those in that matrix can change the behavior. But they're all going to be constants, they're all going to be the same structure, which kind of keeps things relatively focused, which is good for us. So we'll start solving them in the next video. But for now, just you can see how to set up, from a system of equations, set up the matrix equation, and then we can also use that in the kind of examples we've seen before of reducing a higher order equation down to a system of first order ones.